The overall goal of this procedure is to precisely cut the neurons of C. elegans with a laser in vivo. This is accomplished by assembling the axotomy system and precisely focusing, aligning, and adjusting the power of the laser. When worms are immobilized on a microscope slide, their neurons can be cut with precise spatial and temporal control. The extent to which severed neurons regenerate is then measured by scoring for growth cones and/or by tracing neurite lengths.
The main advantage of this technique over existing methods, like the femtosecond laser, is that the micropoint pulsed laser is a cost-effective system that is easy to set up and maintain, and is readily adaptable for a wide variety of applications.
Though we typically apply this method to study regeneration of the GABA motor neurons, the system can also be used to ablate other cell types, such as skin, muscle, or specific neuronal synapses.
This method requires a micropoint laser system. The laser mounts to the epifluorescence port of a compound microscope and includes a single dichroic that matches the fluorophore in the cells to be cut, a pulse generator, and a foot pedal to operate the laser. At a minimum, the microscope should be outfitted with a 100 x 1.4 Na oil objective and a 4 x objective, have a motorized stage with joystick operation, and be mounted to an air table. For illumination, a light supply with light guide and a shutter mechanism is attached to the micropoint laser. The shutter mechanism is useful to reduce the illumination intensity independently of the laser. A camera, which is connected to a computer, requires a frame rate of at least 16 Hz and must operate well in reduced light. The computer requires imaging software, such as Nikon Elements, to view the neurons, drive the camera, and manipulate the motorized stage. When fully assembled, the user can focus the microscope with one hand, move the stage with the other, activate the laser with the foot pedal, and have a clear view of the on-screen image. Cutting neurons in an organism the size of a grain of sand can be challenging. To accomplish this, the laser must be tightly focused in all 3 dimensions. Begin by focusing the Z-plane. Push in the neutral density filter ND16 to attenuate the laser while focusing. For finer focusing, push in both the ND16 and ND4 fluorescent filters. Next, set the micropoint laser to 1 pulse with the switch turned to select, and then move the filter wheel to the appropriate long-pass barrier filter. Now place a mirrored slide on the stage and focus on pinholes within it using the 4 x objective and transmitted light. Once focused, add a drop of immersion oil to the slide and refocus on the pinholes with the 100 x objective. Then use the optical path switching lever to open the camera shutter and open the laser shutter. If getting accurate focus is difficult, reduce the transmitted light intensity so the edges of the pinholes are crisp. To test the focus, use the foot pedal to fire the laser. If the Z-plane is properly focused, a small hole should show up in the mirror. Now focus the microscope slightly above the plane of the mirrored slide and shoot the laser again. This should make an even smaller hole than the first shot or leave no mark at all. The same result should be seen while focusing below the mirrored slide. However, if a larger hole is produced, then refocus the laser with the focus ring on the ablation head. Finally, verify that the hole is still properly aligned with the crosshairs in the eyepiece. With consistent use, the Z-plane focus rarely needs to be adjusted. To focus the laser in the XY plane, make another hole in the mirror and then access the software. In Nikon Elements, initiate the live capture mode in the Acquire menu. In the Measure toolbar, select ROI Editor. Select the double cross tool and drag the crosshairs to align them with the center of the new hole. Click Save ROI and then Exit Editor to resume live capture. To manipulate the stage with the mouse, activate the Mouse XY setting. Now the laser is focused. Reset the neutral density filters to their original position and set the laser pulses from 1 to 10 for future use. First, Prepare a solution of 3% molten agarose in M9 solution and aliquot approximately 5 ml into a 15 ml tube. Place the tube in a 55 to 65 degrees Celsius water bath and store the remainder for future use. Now, use 2 slides covered in labelling tape, a pair of clean slides, and a drop of agarose to make a pad where the worms can be placed. After 30 seconds, the agarose will have congealed. Pipette 3 to 5 microliters of 0.05 to 0.1 micrometer polystyrene beads onto the pad within 10 minutes and quickly arrange 5 to 10 transgenic worms onto the beads with a platinum pick so their labelled neurons are easily viewed. To avoid damaging the worms, carefully set a standard cover slip onto the worms without sliding it around. The worm slide is now prepared for performing axotomies. Using the eyepiece, locate the worms under 4 times power. Refocus with the 100 times objective, turn off the transmitted light, turn on the fluorescence, and switch the optical path to the camera. Use the mouse to center the neuron on the crosshairs. Now fire the laser with the foot pedal. The right amount of laser power will sever the neuron in 1 or 2 pulses. Too much laser power will cause peripheral damage or blast a hole in the worm. To adjust the laser's power, move the attenuator plate. If the laser becomes weak, the attenuator plate position can be adjusted to keep cutting. However, this is likely an indication that the coumarin 440 in the laser's dye cell needs to be replaced. When performed correctly, laser axotomy produces a small break in the neuron. In certain cases, a small scar may form around the site of injury. Practically, between 1 and 3 neurons are cut per animal, but there is no theoretical limit. When finished, recover the worms by removing the cover slip in a direct upward movement, being careful that the worms remain on the agarose pad. Do not slide the cover slip off. Use needle nose forceps to cut out the pad around the worms. Place the pad on a freshly seeded NGM plate containing OP50 and free the worms with 10 microliters of sterile M9. Between 8 and 48 hours after the axotomy, regeneration can be assessed. To do this, remount the healthy worms on 3 to 5 microliters of polystyrene beads and visualize their neurons. In severed neurons, a neuronal stump distal to the cut site will remain. Both the distal and proximal stumps initially retract after being cut, but regeneration is expected from the proximal stump. Regeneration can be scored for the formation of a growth cone. Alternatively, neurite length can be traced and compared. Typically, between 60 to 70% of GABA neurons form growth cones within 24 hours of being cut.
If the laser isn't cutting properly, it is likely because either the laser is out of focus or because the dye in the dye cell needs to be replaced. Also, if you find that the worms are moving around, it is probably because the agarose pad is too moist. We find that pads need to be left for approximately 30 seconds before worms are placed on them to circumvent this problem. In addition, you can try using smaller sized microbeads to immobilize the worms. Finally, if you find that the axons have a beaded appearance, it's likely because the agarose pad is too dry.
After watching this video, you should have a good understanding of how to set up the micropoint laser system, mount worms for axotomy, cut individual neurons, and assess subsequent regeneration.